Ever wondered how we can even exist if the universe is fundamentally simple? A new paper dives into this mind-bending question, exploring the very fabric of reality and what it means for us. Buckle up, because we're about to journey through the fascinating, and sometimes perplexing, world of quantum gravity. At the heart of modern physics lie two titans: quantum mechanics and general relativity. These theories have revolutionized our understanding of the universe, repeatedly proving their accuracy in their respective domains. However, these two giants don't always play nicely together. They clash, particularly in the extreme environments of black holes and the very beginning of the Big Bang. This is where the quest for a theory of everything begins, a single framework that can seamlessly blend the quantum world with gravity. The search is on for a unified theory that incorporates both the quantum properties of reality and gravity. Several contenders are vying for this title, and scientists are constantly probing their limits. But here's where it gets controversial. Testing these theories is incredibly difficult. We often have to rely on indirect methods, like studying black hole collisions, as seen in recent gravitational wave detections. Leading the charge in this grand unification are theories like string theory and loop quantum gravity. String theory proposes that fundamental particles aren't point-like but tiny, vibrating strings. Loop quantum gravity, on the other hand, suggests that space itself is not infinitely divisible but made of fundamental chunks, linked together in loops. And this is the part most people miss. The variety of approaches in quantum gravity is truly astounding. Some theories even suggest gravity emerges from entropy. These theories rely on complex mathematics to reconcile quantum mechanics and general relativity. And that brings us to the core of this new paper, which has generated quite a buzz. The paper, a preprint, meaning it hasn't yet been peer-reviewed, was authored by Daniel Harlow, Mykhaylo Usatyuk, and Ying Zhao from MIT and the Kavli Institute for Theoretical Physics. It delves into the Hilbert space of quantum gravity. Think of the Hilbert space as an extension of our familiar 3D space, but with an infinite number of dimensions. Now, imagine applying this to a closed universe, one that might eventually collapse in a big crunch. What happens is quite peculiar. This potentially infinite-dimensional Hilbert space, when applied to quantum gravity in a closed universe, becomes one-dimensional. The paper's key implication is that such a universe cannot have an external observer. Professor Brian Cox, a well-known physicist, highlighted a particularly intriguing footnote in the paper, stating, "We leave the theological implications of this statement as an exercise for the reader." It's crucial to understand that this paper isn't necessarily proving or disproving the existence of a deity. In this one-dimensional universe, we wouldn't exist either. Instead, the paper explores how an observer like us could fit into such a universe, drawing on principles of holography, where all the information of a 3D object could be contained on a flat surface. While this paper doesn't solve the unification of relativity and quantum mechanics, it may have implications for black hole physics. Whether or not it does, that footnote is likely to become a memorable piece of scientific history. What do you think? Does this paper's concept of a one-dimensional universe challenge your understanding of reality? Share your thoughts in the comments. Are you more inclined to agree or disagree with the implications of this research? Let's discuss.